In this first video for our study of probability, we begin to answer the question, what is probability? I'm sure that you have an informal understanding of that term, and have certainly used it before in the context of an uncertain result or the odds of something happening. Perhaps without ever having thought of it before, you would agree that the term probability is a way of quantifying how likely a random phenomenon is to occur. We connect these intuitive notions with our first definition, where we begin to start pinning down in the context of mathematics what probability is, and we actually define the whole field of probability theory as a mathematical model for chance or random phenomena. What we are working towards in this first chapter is to pin down precisely what we mean by this phrase mathematical model for something we're already familiar with. To do so, we need to come up with a formal structure so that we can make precise in the context of mathematics what we mean by probability. And anytime we introduce a model within mathematics, we need to first establish what the underlying structure for that model is. In the context of probability theory, that underlying structure is given by sample spaces and events. So let's look at their definitions. The sample space for our chance or random phenomena, or in other words, we talk about these more precisely as probability experiments. And all we mean by that is simply an experiment where something is either being measured or observed, and the outcome is random. There's some uncertainty associated with the experiment. So the sample space for such a thing is simply just the set of all possible outcomes. So really, a sample space is just a fancy way of talking about a set. Notationally, the sample space is denoted with a capital S in general, and if we want to talk about a specific outcome in the sample space, then we'll generally denote that with a lowercase s. So the primary structure that we are going to use in modeling probability are sets. The sample space is a set of all possible outcomes, and then we define an event as simply just a particular subset of the sample space. So it may be that we have some criteria in mind that we want our outcomes to satisfy, and we refer to an event as the set of all outcomes in the sample space that meet that criteria. So again, sets are the underlying structure that we will eventually use to define our formal notion of probability. Before we do that, though, let's look at some simple examples to make concrete these definitions of sample spaces and events. For our first example, let's suppose we just take any old coin with two distinct sides and toss it twice. Suppose that we label one of the sides heads and then the other is tails, and we record the result of the two tosses. In other words, we're recording a sequence of heads and tails, so our outcomes are just H's and T's. For example, a single outcome, little s, would be given by HT, where we toss the coin the first time and get heads, then the second time and get tails. For the sample space, we write it by just listing all of the possible outcomes. This is a simple enough example where there aren't too many possible outcomes and the sample space isn't too large that we can do this fairly easily. So again, it's a set. So using set notation, we have curly brackets, and we're just going to list all the outcomes using H's and T's. So we could have two heads on both tosses, our heads tails example above, the opposite order of tails than heads, and then lastly, two tails. Then close the set with curly brackets, and our sample space is just the list of all of the possible outcomes of this experiment where we toss a coin twice. Now, an example in this context of an event could be the event that at least one heads is recorded. In general, the notation for an event is to use a capital Roman letter. So in this case, we use the letter A, and again, an event is just a set. More specifically, though, it's any subset of the sample space. So we'll use similar notation as we used in writing out the sample space. We can list the outcomes that meet the criteria where the outcome has at least one head. So we can look at our sample space and we can see that this first outcome of two heads and then the second two outcomes where we have just one head are all going to be included in the event A. But the last outcome here of 2 tails does not meet the criteria because there's no heads. So A is simply just the set containing HH, HT, and TH. Let's look at another example. In this example, our probability experiment is to record the time in minutes that a car spends waiting for a green light at some particular intersection. Okay, in the context, our outcomes are going to be lengths of time. So instead of using the general notation of a lowercase s, we're instead going to use t to emphasize the fact that we're measuring time. So an example of an outcome in this context would be t equals, let's say, 1.5. This represents the case that a car comes up to an intersection and has to wait 1.5 minutes, or 90 seconds, until the light turns green. For the sample space in this context, we're not going to be able to list every single outcome as we did before, because now there's infinitely many. Specifically, the sample space is going to be all non-negative real numbers, which we can still write in set notation as a set of all times t that are real numbers with the condition that t is greater than or equal to 0. Right? Non-negative because it could be the case that a car comes to an intersection and the light's already green, so they don't have to wait any time at all. But we can't have the possibility of an outcome ever being negative. We cannot have negative time measurements, and so the smallest that t could be is 0. On the other end, theoretically, t can be any positive number. We have no upper bound. For example, what if the stoplight is broken, or the power just went out, and so it's just flashing red? So here's an example where our set of possible outcomes is an interval of real numbers. So we're not listing every single outcome separately as we did in the previous example. Rather, we could write this as the interval from 0 to infinity. These are 2 separate ways of representing the same set of numbers, the same set of outcomes for this probability experiment. Additionally, we can represent the sample space graphically or visually with a number line, where s is all real numbers greater than or equal to 0. Okay, so it's a slightly different setting than in the previous example. Here we have an interval of numbers as outcomes, whereas before we had a list of outcomes. In this context, let's look at an event. Here I've used the letter B to denote the event that a car waits at most 2 minutes for the light to turn green. So here we're restricting the outcomes that we want to consider. And specifically, we only want the outcomes where the car doesn't have to wait more than 2 minutes, which is the same thing as saying no more than 2 minutes or no longer than 2 minutes, right? So let's use both set notation and interval notation to define B. So in the same way that we wrote S, we can write B as a set of real numbers such that, since it has to be in the sample space, because events are just subsets of sample spaces, we know that t can't be less than 0, and the restriction here is that t isn't more than 2. And in interval notation, this is simply just the interval from 0 to 2. Visually, we can draw B on the number line in red here, starting at 0, and let's say 2 is here, going up to 2, and including both of those endpoints. So again, in this context, our sets are really just intervals on the number line. In general, though, a sample space in any context is always just a set of outcomes, and events are simply just subsets of the sample space. So as we can see, sets will play a crucial role in our mathematical model of probability. So next we review some set theory before moving on to our formal definition of probability in the next section.